Math 1314, Tyler Junior College, Section 3.2, Polynomial Functions. In the previous video, we defined the general form of a polynomial function as a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, and then keep going until you get to the end, a sub 2 times x squared plus a sub 1 times x plus a sub 0. And again, don't let the notation intimidate you. This basically says add a bunch of powers of x's, and the coefficients are just named with the subscript to match the power on the x. Although I didn't write it, there were stipulations. The exponents had to be whole numbers, so 0, 1, 2, 3, 4, 5, etc. And the coefficients had to be real numbers, so no imaginary numbers allowed. The highest power is called the degree. The coefficient in front of the highest power was called the leading coefficient. There were two special cases I neglected to mention in the previous video. If you have a constant function, f of x equals a constant, as long as that constant is not 0, then this function is defined to have a degree of 0. However, if the function is precisely f of x equals 0, then it has an undefined degree. It's not super tricky to define why this would have an undefined degree, but this would have a degree of 0. If it's a constant term, then the last coefficient the last term is the only term. So it makes sense to call that a degree 0. You can think of it as saying that if you're a constant function, then all of the other coefficients are 0, so they don't get to determine the degree. But if every coefficient was 0, including the last one, then who gets to determine the degree? The answer is nobody, because it doesn't have one. So these are very special exceptions, but in general, the degree is the highest power. In this video, I'd like to talk about the characteristics of graphs of polynomial functions en route to actually graphing them. For a parabola, which was the previous section, it was pretty predictable. Or rather, I should say, for a quadratic function, the graph was pretty predictable. It was a parabola. But for a generic polynomial function, there are some things we can say. Number one, the graph is continuous. So what do I mean by continuous? Well, continuous, loosely speaking, means that you can draw the graph without lifting your writing utensil. So for example, that is continuous, it's not broken. An example of something that's not continuous, well, we've seen a graph that's not continuous, the graph of the reciprocal function. F of x equals 1 over x. Do you remember what that graph looks like? It had a branch in quadrant 1, a branch in quadrant 3, and there were two asymptotes, a vertical and a horizontal, on the x and y axis. But this graph is broken. You can't draw it without picking up your writing utensil. There is a much more rigorous definition of what it means for a graph to be continuous. But at this level, it suffices to say that if your graph is broken, or you can't draw it without picking up your writing utensil, then it is not continuous. So the graphs of polynomial functions are continuous. They won't have any breaks in them. Number two, the graph is smooth. What smooth means loosely is no sharp corners. No sharp corners. Now you can wiggle all you want. You can start off coming in high and then do a little wiggle, up, down, and then I almost made it not smooth there. But as long as there are no sharp corners, for our purposes, that's the definition of smooth. And again, there's a much more rigorous definition to what it means for a graph to be smooth. We'll save that for the calculus class. Now, do we know a graph that is not smooth? Yes. The graph of f of x equals the absolute value of x was a v. It's almost smooth everywhere. It's smooth almost everywhere except the corner. So the graphs of polynomial functions will not have sharp corners. So no breaks, no sharp corners. And this last one is about how many times it can turn. For a quadratic function, it will turn exactly once. If it's a parabola that opens up, it decreases and then it increases. So it turns or changes direction once. If it's a parabola opening down, it increases and then decreases. So it turns once as it changes direction vertically. But you can predict the number of times the graph of a polynomial function will turn based on its degree. If the degree is n, then the graph can turn at most n minus 1 times. Now, it doesn't have to turn that many times, but it can. It can also turn fewer times, but if you go fewer, you have to reduce that number by an even number. So, for example, if the degree was 5, then that means we can turn at most, I can't spell today. We can turn at most 5 minus 1, which equals 4 times. So what would it look like if a graph turned at most 4 times? Well, it could turn 4 times. So we'll start high and turn 4 times. 1, 2, 3, 4. So it could look like that. 1, 2, 3, 4. Now that lesser by an even number is basically because you can compress part of the graph so that one of the high and low points flatten out and it's no longer either. So for example, imagine that we kind of go squish right here and we lose both of this high and this low point. So it could turn 4 times, or it could turn 4 minus an even number, like 4 minus 2. 4 minus 2 is 2. So we could turn twice, once, twice. It is possible for a 5th degree polynomial function to only turn 2 times, or even less than that. If the most number of turns is 4, most number of turns is equal to 4, or we could lower that by an even number and turn 2 times, or we could lower it by a bigger even number and turn 0 times. Now, how can a function like this possibly turn 0 times? Well, it can still be curvy, but never change direction. So the degree predicts a maximum number of turns by subtracting 1 from it. So 5th degree could turn 4 times, an 8th degree polynomial could turn 8 minus 1 is 7, or lower it by an even number, or lower it by an even number, or lower it by an even number. So an 8th degree polynomial function could turn 7 times, or 5 times, or 3 times, or 1 time. So one thing you can say about even degree polynomial functions, they all have to turn at least once. Think about it. Not true for odd degree.